I'm sorry, I yell 15 hours a week. It's my job. A room full of people, so I don't really need the microphone. But anyway, I'm here to introduce Weston Henry. Weston and Spencer, who will come up later, both had similar projects. The idea was that at Sonoma State has what's called a maker space. They've joined the maker movement, where we have 3D printers, computers, other tools to easily prototype various things which would have been extremely difficult to build the old-fashioned way by taking a block of aluminum and drilling holes and carving, etc. Now you just build it up as layers using a computer CAD system. And so they both came to me wanting things to do this semester, and we sort of brainstormed together the idea of building things, you know, using the 3D printing that have unique physical properties that would be difficult to do any other way, but are actually fairly, you know, not too difficult. Wes had the additional challenge that what we were building with him was an acoustic structure, and we don't really teach acoustics here. So he had a lot to learn while doing it, and he did an excellent job, I think. Thank you.
All right, so the title of my project is Sound Absorption from Acoustic Metamaterials. So the first slide, it's a basic about sound. So what is a sound wave? A sound wave is a pressure wave, and it's caused by a vibration in an object. So there are high parts of pressure right here. So you see all the molecules are really close together, and that's called compression. And then there's decreased pressure right here, and that's called a refraction. So there is so these are longitudinal waves. So when a sound wave is produced, the molecules move left to right rather than up and down. So that's how this works right here. And then there's a relationship between the frequency, the speed of the wave, and the wavelength, which I will go to in a little bit. So here's just a quick video. You see a vibration of this red right here, and then you see the compression move along right there. So what is a metamaterial? A metamaterial is a field of science that has greatly expanded within the last 20 years or so. We've come out with a lot of applications for these. So these are all man-made structures, and they have physical properties based on the shape and the arrangement of the structure. So all these will do different things here. So some of these properties that they could affect would be acoustic properties, which I'm going to talk about, optical properties and thermal properties and things like that. So an acoustic metamaterial would be something that manipulates the sound wave, and we would be able to control it. So there's two types of current sound absorption, and these are porous materials and microperforated plates. So on the left here is a porous material. You see a whole bunch of holes right here. So what those are is when the sound wave interacts with these, it causes them to vibrate a little bit, so it loses a little bit of the acoustic energy into heat, and then also the friction as the wave travels into it, it loses some of the energy due to the friction that way. So these are velocity based. There's particle velocity, so that is how they absorb this. So depending on the speed of the wave, it will get more absorption here. So there's microperforated plates, and these are pressure absorbers. So it depends on the pressure of the wave, not the velocity of the wave. And how these work is when the sound goes, it goes into these holes right here, and it interacts with the material, and there's friction. So the sound wave also loses it to friction that way. The thing with the microperforated plates is there's a small gap behind there where the air gets pushed in, and I'll talk about this a little bit more in a sec, and then it comes back out. So it oscillates in between the holes, and it loses energy that way. So it has to do a lot with pressure instead of the velocity of the wave. So a little bit about my project. Mine is a lot more similar to the microperforated plates than the porous materials. So in the microperforated plates, those are just straight cylinder holes. So for my project, what I'm doing is I'm doing a helix shape. So instead of just going straight through, it winds around and it takes more time. And since there's more surface area with a helix than a cylinder, there's going to be a lot more absorption due to the more friction. So I had to create a structure with more friction. So to do this, I had to create this in a CAD software, Tinkercad, and then I had it 3D printed here on campus in our makerspace. And also part of my project was to build a standing wave device that tests these samples. So part about my design, I have 3 separate samples, and so the tube diameter is this right here. So I only varied one parameter, and that is the tube diameter. So I have it at 1.2, 1.4, and 1.6 millimeters. All the other dimensions of the helixes are the same, so it keeps it constant and keeps my testing results a little bit better. So the spacing between, there's 5 spirals. The spacing between the spirals is 2 millimeters. In the second photo here, you could see a helix array. So there's 21 helixes there all together, and they're spaced out 5 millimeters apart. In the third picture right here, that's kind of like the final design of it in the Tinkercad. So it's a solid, the orange is a solid area, and all the little gray dots you see here are the holes to the top of the cylinders, or to the helixes. So on the bottom there will also be holes so that the air could travel all the way down through it. So the main part of the main physics behind this is the Helmholtz Resonator, and what a Helmholtz Resonator is, it's an object with an open hole at one end and is closed on the other end. And it acts very similar to a mass on a spring. So what happens is, we all know, well, maybe not all of us, but a lot of people with the mass on a spring, we know if we compress it, it's going to want to go back to its equilibrium position. And due to that, there's a momentum with the mass. So it goes past the equilibrium position, and then it oscillates back and forth. So before it stops, it will oscillate past its equilibrium position. So this works very similar. So right here, that's like analogous to the mass on the spring, and the volume right here is the spring itself, the stiffness of it. So as air gets directed into the cavity, it's going to compress all that, and then it's going to want to go back to equilibrium, so it pushes it back out, and then there's an oscillation in the air. So my port, my neck right there, is my helix design, so that every time it goes in and out, it goes through the helix and it loses energy that way. So there is a resonant frequency, and that's when the amplitude of the oscillation is at a maximum. So it's not the speed of the oscillation, it's how much it actually oscillates. And then I have a little video here. It might be hard to see, but there's a little gray area right here that represents the air in the cavity. So you could kind of see it go up and down. I don't know, maybe people in the front row can. But you see the pressure inside go up and down, so there's that. The next part I'm going to talk about is standing waves, and standing waves are the most important part of this because it's how you test the absorption of it. So what a standing wave is, it is a wave that oscillates in time, but the peak amplitude stays in the same place the whole time, and I could show a video right here in 1 second. So how these standing waves are created is it is constructive and destructive interference between two waves traveling in opposite directions. So you can kind of see here, the incident wave travels and it's going to hit this right here, and then there's a reflected wave going back, and you could just see the amplitude going up and down that whole time. And so with standing waves, there's something called harmonics, and how a harmonic is defined is the amount of wave that it travels before it gets reflected. So on the first harmonic, you could see a half wavelength, and then it gets reflected. Second harmonic is a full wavelength, and then it gets reflected. So I'm going to show this in a sec, but I'm going to have my material right here, and since it absorbs sound, the reflected wave is not going to have the same amplitude. So this is a schematic of my testing device. So there's a speaker right here that produces the initial sound wave, and it produces a standing wave here, and then there's a reflected one right there, and this oscillates up and down the whole time. So this is where my sample is going to be, that's where my helix design is going to be, and then behind it is my Helmholtz cavity. That's where it's going to oscillate at. So I created 7 different Helmholtz cavity sizes ranging from a 1/2 inch to 3.5 inches in increments of a 1/2 inch. So there's something called a standing wave, and that is the ratio between the amplitude of a standing wave and the minimum of a standing wave. So what's happened is I'm gonna produce a 343 hertz sound wave. So back on the first slide, I talked about the relationship between wavelength, frequency, and the speed of the wave. So the speed of sound in air is around 343 meters per second, and frequency is measured in per second. So it's going to be exactly 1 wavelength. So I created it so this is exactly 1 wavelength here. So the standing wave is a lot easier to create. So from here I have a microphone at the maximum, microphone at the minimum. I'm able to calculate the standing wave ratio, and from that I'm able to calculate the absorption coefficient. So this is like a physical, my physical design. So I have the function generator right here connected to a speaker, and I have a microphone at a half wavelength, or a quarter wavelength and a half wavelength, and it travels all the way down, and I'm going to have my sample right here, and those are my different Helmholtz cavity sizes. And that is what my actual sample looks like. Those are the little helix holes that it travels through. So for my data, this might be a little bit hard to understand, but the green is where my second mic was, so that would be where the maximum is. If you remember from 2 slides back, that's where the maximum is. And then my red is where the minimum is at. So this is measured in volts because that's how we measure pressure with the instruments we have here. So I have 3 separate samples, 1.2 millimeter, 1.4 millimeter, and 1.6 millimeter. And this is just the increasing cavity depth. So the first one starts at 0.5 inches and goes all the way to 3.5 inches. So I'm easily able to calculate the standing wave ratio from this information. So from here, I was able to calculate the absorption coefficients. So in the 1.2 millimeter helix, you could see some oscillation here from 0.74, 0.70, 0.71. And that's actually what we want because there is going to be a certain volume where the absorption is at a maximum. So we know it's somewhere between 0.05 and 2 inches. Compared to the 1.4 and the 1.6, you could see these numbers just constantly increase the whole time. So the reason behind that is the cavity size was too big. So we didn't actually get any resonance frequency. We don't get any oscillation between the sample itself. So those are increasing. So on paper, it looks really good. You got like 98% absorption, but that's not actually what's happening. So every time a sound wave interacts with a surface, some of it gets transmitted and some of it gets reflected. So the reflected part is from the standing wave, and then part of it gets transmitted through the material itself. And the reason why these are so high is because the part that's reflected from my material and then the part that's reflected from the back cavity, those are in separate phase, so when they both reflect, they cancel each other out. So it looks like it got a lot of absorption, but it all just actually got transmitted through the actual thing. So conclusion, for the 1.2 millimeter, there was some distance between 0 and 2 inches that it would obtain the most amount of absorption. With the 1.4 and 1.6, the cavity size was too small to get any real absorption, any real data from that. So the next step would be to finely tune the Helmholtz Resonator cavity size. So I did it in increments of a ½ inch, but if there would be a way to do this in the size of like a quarter or a tenth of an inch, it would get a lot more data. You would get a lot more accurate data, and it would be a lot easier to find the actual volume of this. And also, smaller, what you saw with the 1.2 seemed to work a lot better because there was some oscillation there. And that actually makes perfect sense because with the smaller helix diameter, there's actually going to be a lot more friction with the air molecules. It would be like a whole bunch of people sliding down a slide. And if the slide's really wide, it would be a lot easier to transmit. But if the slide's really narrow, then people would get stuck a lot easier. So it's kind of like that. And then alter the number of helixes. So this would you would be able to add helixes and see how that changes the absorption coefficient, subtract, and see how that does as well. So I'd like to thank Dr. Jones for mentoring me through this research, and also Ryan Brown for helping me set up the experiment and all that. So.
Questions for Weston?
Tweety.
Why did you choose helically spiral tools for your?
So in the regular micro-perforated plate, it's just a regular cylinder. So with the helix, there's a lot more surface area inside of it. So there's going to be a lot more friction that it interacts with as it spirals down, and that's going to slow it down and increase the absorption with that. Jake?
Did you try to vary the thickness of your metamaterial at all?
So I started off with 10 spirals, but that was just it was just like too thick that it would like barely have any absorption at all. So you had to make it smaller so that there was at least enough air to get through it to have some oscillation between the sample. All right.
Let me just one more. Okay. I think based on our
Oh.